I'm presenting the my topic, which is the removal of pharmaceuticals with the help of this MgUL2 modified triaceous biochar. So in this presentation, I will try to cover my major focus will be on the remediation aspect. But what are those pharmaceuticals? They come under the category of emerging contaminants, and what are the sources of these pharmaceuticals into water, especially in water body, and their remediation. In remediation, I will try to complete the preparation of the that particular adsorbent and its characterization, its sorption studies, and try to give the possible interaction of these contaminants, pharmaceuticals, with the adsorbent. So the pharmaceuticals comes under the category of emerging contaminants. So what are these emerging contaminants? So these emerging contaminants are the substances which are not usually monitored or regulated in the environment, but they have potential adverse effects on human and or environmental health. So if we divide these in emerging contaminants, so they are like pharmaceuticals, personal care products, pesticides, hormones, fire extinguisher, industry products, and several more. Like even you have heard about the micro and nanoplastics. So my entire focus will be on the pharmaceuticals, and so the pharmaceuticals presence have been seen on every continent, and also all type of water, including surface water and other like the wastewater treatment plants, effluents. Different water bodies have shown a significant percentage of these pharmaceuticals. And if we further elaborate or classify these pharmaceuticals, so we can classify them in like NSAIDs, antibiotics, anti-epileptic, antidepressant, anti-allergic. There are more. So in our study, we have chosen this acetaminophen, which is also known as paracetamol, and antibiotic, which is trimethoprim. So the reason behind the selection of these two drugs is that the pharmaceutical like acetaminophen is very frequent, and which is used as a pain and for mild fever relief. And if we talk about the trimethoprim, so trimethoprim is also antibiotic, and it is an antibiotic and used in a respiratory or urinary tract infection to deal with those things. So how these pharmaceuticals are coming into the environment? So there are three major sections from which it is coming to our environment. The first one is the pharmaceutical manufacturing companies which are making these pharmaceutical, and you will get high concentration of these pharmaceuticals into their effluent. And the second one is the human medical compounds what we use, which come to the sewer system, and also the veterinary for the cattle and all. So ultimately, they go to the landfill and different treatment technologies like hospital effluents, industrial effluents, and from there they go to the wastewater treatment plant, and from there they further infiltrate into the surface water as well as the groundwater, and it will ultimately come to the consumer, and it will show their harmful or negative effect as stated. But why these pharmaceuticals are problematic? So the first question is that the first reason is that these pharmaceuticals are unregulated. There are no such regulatory body, or there are no such standard which define that what should be the concentration of these particular pharmaceuticals in different type of water body. Except I think Australian government has made a pharmaceutical like some kind of guideline standards, and they have categorized into first one is ADI, what is acceptable daily intake, and the for these pharmaceutical concentration in drinking water guideline. So for trimethoprim, they have given the limit, which is 20 microgram per kg per day. For paracetamol, they have given 50 microgram per kg per day. This one is as ADI, acceptable daily intake from whatever you are eating. But in drinking water, they have given the unit is microgram per liter. So 50 microgram per liter is for trimethoprim, and 175 microliter for the acetaminophen. So these are the problems. Like there are only, I think, Australian guidelines are there. except that I didn't find anything. So these are the problems. So we have to deal with it, and for that the objective. So let's start with the preparation of my adsorbent. So first we develop our this biochar using the rice husk, and preparation of this biochar, we got that the acetaminophen and trimethoprim are not very good. The removal percentage was not very good on these plain biochar or simple unmodified biochar. So we had to go for the modification part, and the modification part is given in the solid line bracket, and the dotted line represent the synthesis of simple biochar. So we choose two temperature to see whether the pyrolysis temperature are affecting the removal efficiency. So in second B category, the solid line bracket, you can see we use rice as biochar and kept them a particular size from 50 to 150 bases, which is equal to 0.3 to 0.1 mm, because we need to enhance the surface area. To for that we have to minimize the particle size. When we treated it with magnesium and aluminum hydroxide, and we precipitated using the sodium hydroxide and sodium bicarbonate, and aging was done at 90 degrees Celsius for 24 hours. So we got a slurry of biomass which is engineered with this magnesium aluminum salt, and then further it was pyrolyzed, same condition as it was pyrolyzed for the biochar, simple biochar preparation. So we got the biochar as well as the this MgO-L2 modified, or we can say engineered biochar. Now the if we see the properties of this biochar, so the property of biochar, if you see, the yield is increased from 24 to 33. The carbon content got reduced. We got the ash content increase. The PZC, the adsorbent net positive net surface charge also get increased, as well as the surface area. So these are the parameters which are required to eliminate those pharmaceuticals from the water. Now we also perform the EDXRF, the elemental analysis, like what was the concentration of these metals in the biochar as well as its modified version. So we got that the biochar, the metal concentration increased from 1095 ppm to 2.2%. So the first one is in ppm. So like if you convert the ppm in percentage, so it will be 0.1 ppm to 2.2 percent, 0.1 percent to 2.2 percentage for mg, as well as the aluminum concentration also got increased from, it was not detected, to 0.8 percentage. Similarly, the amount of silicon was also, silicon got reduced. Okay, so from that we also perform the surface morphology using SAM and TEM. So we can see the surface morphology. There are porosity, there are pores in the biochar. The A represent the simple biochar, and B is the biochar which is modified biochar. And we also see there are some rough structure, roughness on the the figure in the figure B, which is the modified biochar. And the TAM analysis we can see in the C and D. The C represent the biochar and D represent the magnesium aluminum modified biochar. So in this C version, you can see this thin sheet of this graphitic carbon of biochar, and also if we impregnated it, we got the mixture of this aluminum magnesium oxide with those biochar. Now if we see the EDX mapping, we can say that the concentration of this aluminum and magnesium were below detection limit in the biochar, but it got increased 0.54 for aluminum and 1.6 for magnesium. So the interest was our interest was to prepare these biochars. So we can say that what we were asking, we got the result. Now to further confirm this thing, we also went for the FTIR and the XRD analysis, spectroscopic analysis, and we performed this analysis for plain biochar, its modified version, its like ACM and TMP laden version for both the FTIR and XRD. So in case of biochar, you can see the unpyrolyzed biochar and engineered biochar, you can see there are some peaks of the hydroxide at 3450 centimeter inwards, and as well as in 14-15 centimeter you get the carbonate stretching band. So after pyrolysis, these bands these bands got removed because at higher degree of pyrolysis, the carbonate becomes CO2, as well as this water, these also get evaporated within the pyrolysis. And after the absorption of this ACM is short form from acetaminophen, and TMP for trimethoprim, the surface become more the spectra become more planar because they have taken the place at the upper surface. So we couldn't see that much of the functionalities. But similarly, you can see in case of the XRD, the biochar was majorly the graphitic carbon as well as the silica, but after the mixing of this biomass with the Mg and Al salts, we get this typical LDH structure, which is 2 theta degrees, 11, 23, 35, 45, and 60 around. But after pyrolysis, it got converted into the magnesium oxide and aluminum oxide, and the amount of silica got reduced. And after the addition, after the sorption of pharmaceutical like ACM and TMP, these phases also become become very minute, or they vanished. So it means the deposition of pharmaceuticals are there. That's why we are getting this. Like after preparation of this, we had to check whether the what we try to do to impregnate this biochar with the magnesium aluminum salt. So we had to check the at what pH we had to perform this leaching test to study whether these attached aluminum and magnesium are still there from 2 to 10 pH range or not. So we performed this, and we found that the for both cases, magnesium and aluminum, the leaching of these magnesium and aluminum were higher at lower pH, at 2 pH, as you can see, but at higher pH like 4, 6, 8, 10, there was no such leaching. And we also compared it with the Bureau of Indian Standard 2012 drinking water standard, and we found that the for aluminum, the acceptable limit is 0.03, and for immiscible 0.2. So all these biochar, they have the leaching was within the permissible limit for aluminum, and for magnesium it was within the permissible as well as the acceptable limit. Further, we also study the effect of pH on this sorption. So the right one is the acetaminophen sorption, and the left one is the trimethoprim sorption. So as you know, the pH plays a very key role in this sorption process. And if you see the red color represents the removal efficiency of pharmaceutical. I'm talking about the figure 1A. If you see the pH, the sorption remains more or less same from 2 to 10 pH, but after 10 it started decreasing. But if you see that there is a red line which represents the equilibrium pH. So if you see the pHC of our developed biochar, which is 9.7, it means the adsorbent have net positive charge above the below the pHC, and above the pHC it got net negative charge. So after the means 9 above 9.7, the surface become negative. But if we see the acetaminophen's acid dissociation constant pK value, which is 9.4, so our acetaminophen remains neutral up to the 9.4 pH, but above it started deprotonating and it becomes negative charge. So that might be a reason for electrostatic repulsion between the developed adsorbent as well as the acetaminophen. That's why this reduction trend was there. But if we see the pH effect of pH on the trimethoprim, so in the case of trimethoprim, its pK value is 7.12. It means this trimethoprim remains protonated below 7.2, 7.12, and it get deprotonated or become neutral above 7.12 pH. So in case of you can see the initial pH, at initial pH like 2, 4, 6, the sorption like removal efficiency were lower, maybe because of the positive repulsion between the adsorbent and the trimethoprim. After that, we performed the kinetic study, and we found that this option was the equilibrium was achieved within 6 to 8 hours. And we also fitted these data to the obtained data to the pseudo first, second Elovic and IPD model. These are the results for those models. And after that, we can see that the Elovic model was base fitted here. So Elovic model base fitted, it means that it supports the chemical interaction, like, and also support that the strongly heterogeneous, the nature of adsorbent is strongly heterogeneous. We also performed the isotherm test, and in isotherm study, we took the concentration from 0 to 200 ppm for acetaminophen as well as for trimethoprim, and we plotted it using these Langmuir, Tramkin, Friendly, different models to get these numbers. And we found that the sorption capacity, if we see the monolayer Langmuir sorption capacity, is increasing with the rise in the sorption temperature, like from 10, 25, and 40. This rise in sorption capacity with increasing temperature is telling us that the process is endothermic in nature. It was given, like, it was obtained in both, like, acetaminophen and trimethoprim, and the sorption on trimethoprim is more compared to the acetaminophen, what we observed from this. And also we can conclude that the all models, their R square, the fitting value is higher, like above 9.5. So we can what we can conclude from this, that these support that the homogeneous, monolayer, multilayer, heterogeneous option are simultaneously taking place. So we cannot conclude a single mechanism for this absorption. It is like there are multiple processes are going on for this sorption. And further, we also try to see the effect of competing ions on this sorption of acetamino and trimethoprim. And we check first the ionic strength from 0 to 50 kcl, millimole kcl, and also different cation and anionic mixture. And we found that at overall, we can see that there are no such greater impact of this competing ion on this sorption of trimethoprim and acetaminophen. So we can use it for the real water problem. So to get a look into the real water, we also performed the tap water. So we took our tap water from lab, and we maintained the pH. Like the overall, if you see the pH study, we performed all study on pH 6, which was optimized using the pH study. And the tap water, it has the pH of 8. So we performed the sorption at pH study, optimized pH study 6, as well as the unadjusted pH, which was the natural pH of tap water. And we found it was more or less okay with the double distilled water, means the original what we got in pH study, it remains same in the presence of different competing ions. Further, apart from this batch study, we also perform the column study. So column study are important to get a real scenario, what we can do, how and what we can remove the moving water in a column. So here we performed, and we found that similarly, like we mentioned in the batch option, the capacity for acetaminophen was lower compared to trimethoprim, and we got the same trend here for the column study. These are the parameters which was taken into consideration for the column study. And after column study, we also perform the desorption and regeneration study. It is also important because the regeneration of adsorbents is necessary. If we regenerate it several times, so we can reduce the cost of this production of this adsorbent. So we can use it multiple times. So we went for different, like, ADTA acids and alcohols, and we found that our developed engineered biochar is robust, and it gives good removal capacity up to 3 cycles for ADTA, HCl, ethanol, and methanol. And now we come to the mechanism part. What would be the mechanism what would be the possible interaction of these pharmaceutical with biochar and this MgO and aluminum oxides. So we know that the pore diffusion is a well described interaction for the pharmaceutical on those surfaces which are porous. So we also give an idea, a representation of pore diffusion. This will be this is a possible reaction interaction, and also we went for uh, the individual, like if we have biochar, we have magnesium oxide, we have aluminum oxide. So we try to conclude all these three in our interaction portion. And for that, here you can see the if A represent the pK value, means protonation deprotonation of the acetaminophen, and D for the trimethoprim. So if as I shown you in the FTIR section, we have a surface carbonyl group. So there are possibility that these biochar is also playing a key role in the sorption of these acetaminophen and trinethoprim using this hydrogen bonding as well as the pi-pi interaction. The role of MgO, L2, aluminum oxide, Al2O3 was also established, and we went for the further exploring the pK value of this Al2O3, and we found that the Al2O3 present on the adsorbent is also dependent on the pH. So if the pH remains below 5.3 or 6.2, the aluminum got protonated, it becomes ALOS twice positive charge, and between pH 6.2 to 9.9 it remains neutral, means aluminum in form of aluminum hydroxide, and at higher pH it also get deprotonated and becomes negatively charged. So we try to see what can be happened with the similar pH of this acetaminophen as trimethoprim. So we found that the hydrogen bonding is taking place in case of acetaminophen, trimethoprim, and as well as there are some repulsion which I have told you in the pH study, pH section, like there are some repulsion. So repulsions are taking place for the acetaminophen at pH above 10, for trimethoprim at pH below 5.3. And further, the role of MgO crystal was also assigned, like MgO remains, protonated below pH 5. It remains neutral MgOH between 5 to 12, and it becomes magnesium oxide negative, net negative charge at pH above 12. So similarly, we check the possible interaction with this trimethoprim and acetaminophen, and we found that the hydrogen bonding between these functional groups and also the repulsion, the electrostatic repulsion is taking place, as you can see in case of B and G, but C, D, and B, E, F are showing the hydrogen bonding of acetaminophen as well as the trimethoprim. And I think I'm within time. This is the conclusion. What we have concluded, that the preparation, the successful preparation was done of this biochar. Also, we can see the our adsorbent is stable in this working pH, which is the 6 pH. The high capacity of aceta and trimethoprim was achieved. The pharma was also able to remove the developed adsorbent was also able to remove the pharmaceuticals from tap water, and also the regeneration was done and carried out for 3 cycle, and we found good result. So we can say that the developed adsorbent is robust and it can be useful for the other spectrum, other pharmaceuticals which are lies in same category like NSAID and antibiotics. Thank you.
Thank you very much, Abhishek, for your very comprehensive study. I guess that was the big part of your PhD.
Yeah.
So I have one starting question. Where's the silica Where do you think it went?
Yeah. So the silica, we treated our biochar with sodium hydroxide at a temperature like 90-95 degrees Celsius. So there are possibility that this at basic pH, this silica got react with the NaOH and form the sodium silicate. And we also washed it several times, so it may have washed out from the biochar. That's why there was some reduction of silica.
Okay. So John Hoffmeyer was asking, did you compare your metal dope biochar with commercial activated carbons in your study?
No, actually, I compared it with the unmodified version, the only rice husk biochar. But in literature, I compared the capacity, so we found that the not that much, but we have a comparable result for this acetaminophen and trimethoprim removal.
Okay. And what would you could you, or I'm not sure if you have done it, but could you estimate how much your biochar, your modification process adds to the cost of biochar?
Cost benefit, no, I haven't done cost benefit analysis, but I have to do. Yes.
From your feeling, do you think that's something you can do on a large scale?
Yeah. We can do it because the what we are using rice husk, and we are using the aluminum and magnesium salt, which are relatively cheaper than other chemicals, so we can go for large scale.
Okay. Interesting. Paul Anderson has a question. Please repeat the conclusion about recycling of the biochar, and what the advantages of regeneration, I think he means.
About the regeneration.
Yeah, because there's always the question. I think I'm not sure if I don't want to answer for you, but why regeneration of biochar might be useful, I think.
Okay, so actually what happened, if we use biochar for single time, like for one time use, so we will use and we will discard it. But if our biochar have the capability to go for several adsorption desorption cycle, so we can reduce the production of another batch of this adsorbent. So it will be helpful to first of all, it will save time. We can use it again. It will also affect the cost. We don't have to go for another set of preparation. So all chemicals and all things. Yes, we have to use a eluent or desorbing agent that can be helpful in regenerating those biochar adsorbents.
So, and do you know how much regeneration agent do you need to desorb your?
So in my case, what I have done, I took 0.1 gram of adsorbent and mix it in 25 ml of eluent, like where is this? 0.5 ml of element of EDTA, SCl, H2SO4, and these alcohols. And I mixed it, and then I left it for 4 to 6 hours, and then I filtered it and I dried it and again went for the same adsorption.
Okay. And just out of curiosity, did you try thermal regeneration as well?
Pardon me, I couldn't.
Thermal regeneration, like heating it up.
No, I haven't done the thermal regeneration.
Okay. And I guess if there are any heated, Paul and Ronald, did that answer your question? Okay, great. Otherwise, I think if you go to slide 30, I think we can see your publications on that. Yes.
No, I haven't mentioned the publication, but I have 9 to 10 publication right now. I haven't mentioned it. I gave it the references.
Okay, but at least we see the reference for the paper, so we have it in
Yeah,
the recording if anyone wants to read through it.
Yeah, that one is the first one is my article, which I have published recently, and all the other information is also there in there. These collides and surfaces, a physical, chemical, and engineering aspect.
Okay, great. So thank you very much, Abhishek. Great.
Thank you.
And I wish you all the best for the rest of your PhD. I guess that you're finishing soon.
Yeah, I'm about to finish in December, and I'm looking for postdoctoral opportunities.
Okay, so if anyone here has a position open, contact us,
Yeah.
Abhishek, soon.
Yeah, that would be great.
Okay, thank you very
Okay.
much, Abhishek.
Thank you. Thank you.
And so that was our first session of the webinar. So